Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning to all my students. Okay, for today and this week, we will look into these special topics called dimensional analysis and modeling. Okay, it is our chapter number 7. Okay, what we have here. Okay, in this particular chapter, we have 5 subtopics that we will look into. The first one is the dimensions and unit. Second one is dimensional homogeneity. The third is dimensional analysis and similarity. And the most interesting part is the next one is the method of repeating variables and the Buckingham Pi theorem. And the last one is the dimensionless term. Okay, before we proceed our lecture today, I would like to highlight that this particular chapter is very useful for your analysis, okay, especially when it comes to develop or to look into something that is too big to be analyzed or something that is difficult to model. Then this particular chapter might be helpful for you to understand the problems and how to deal with it. Okay. Okay, for the dimension and unit, okay, dimension is a measure of a physical quantity without numerical values, of course, while a unit is a way to assign a number to that dimension. Okay, there are two different items that being discussed here. Again, dimension is a measure of physical quantity, while unit is a way to assign a number to that dimension. For example, length. Length is a dimension that is measured in units such as micron, feet, centimeter, meters, and kilometers, etc. Okay, and there are 7 primary dimensions, also called fundamental or basic dimension. Okay, the first one is mass, length, time, temperature, electricity current, amount of light, and amount of matter. And for fluid mechanics, normally or usually we only deal with number 1 until number 3, or sometimes we also interested to look into number 4, okay, which is mass, length, time, and temperature. Okay, I have a footnote here in the box here. Okay, primary dimensions are defined as independent dimension. Remember, it is independent dimension from which all other dimensions can be obtained. For example, I give you a simple example, which is speed. Okay, sometimes you refer it as velocity if you are dealing with a vector component. Okay, when you are talking about speed or velocity, the unit is, okay, it is the meter per second. Okay, meter per second, where meter is the length. Okay, meter is length and second is time, right? Okay, you have for the speed, we have meter per second. So it is our m and it is our s, right? So there are two dimension involved here, okay, from this primary dimension. Okay, primary dimension and their associated primary SI, okay, and English unit is shown in this particular table. That the mass, normally we use m, length is capital L, time is small t, and temperature is capital T. Okay, and electric current is I, amount of light is C, which is candela, amount of matter is N or mole. Okay, it is the SI unit, and on the last column here is the English unit. Okay, and not to forget that some other books might use a different symbol. Okay, as you can look down here, I have one particular table where there are two different books, for example, from White and the other one from Chengal Cimbala. So in this particular book, you see there are slight differences. For example, for mass in the book by White, it is capital M, whereas in the book by Cimbala, it is a small m. Okay, and also this part down here. So what you need to do is make sure that you must be consistent during your analysis. That's all. Okay, you can use either of these annotation or symbol, no problem, as long as you know what it is and you are consistent in your analysis. Okay, but to me, I would prefer to look into the last column here. Okay, for our class, for example. But no problem, you can also refer to this one. Not a big deal. Okay, all non-primary dimension can be formed by some combination of 7 primary dimension, like I just showed you just now, where the speed it is, the dimension is meter per second, right? Okay, so there are 2 primary dimension involved, which is the length, which is m, and the time, which is it is s lah, meter per second. So, for example, another example here, force has the same dimension as mass time acceleration. Okay, this is by Newton's second law. Force, as we know, it is a product of mass and the acceleration. Thus, in terms of primary dimension, you can look at it as like this, where force, you have mass, and acceleration, you can further expand it, where acceleration is meter per second square, right? So meter is the length and second square is the time. So you can replace something like this. And therefore, from there, you can further refer to this particular table. Okay, you can refer to this M, L, small t, and capital T, this symbol here, to replace all these. M is the mass, capital L for the length, and small t for the time. Okay. Okay. A unit is actually a way to assign a number or measurement to a dimension. Okay. There are 3 primary unit systems in use, which is the International System of Unit, SI, where normally we use kg, Newton, mass, second, Kelvin, etc. And the English engineering system or of units, commonly called English unit, we have a pound, mass, pound, foot, second, and others. The British gravitational system of units, BG, we have a slug and rest. Unit must always have numbers associated with them. For example, length is a dimension, but it is measured in unit of feet. Okay, or meters for the SI unit. Okay. Okay. Another example here. For example, length is a dimension, but centimeter is a unit. Okay. Example number one, we have an engineer studying how some insects are able to walk on water, okay, or to stay on water. A fluid property of importance in this problem is surface tension, okay, which has dimensions of force per unit length. Write the dimension of surface tension in terms of primary dimension. Okay, as we have learned in our early, if not mistaken, chapter number 2, okay, where the surface tension, it is a product of force and divided by length. So what is force? As what we have seen just now, force is actually a product of mass and the acceleration, right? So m for the mass, L for the length, and T for the time, and divided by the length again. So from here, you can further simplify this into m over t squared, in which this particular L, you can cancel them out. Okay. And for these variables and constant, we have dimensional variables, we have dimensional constant, we have pure constant, and we have angles and revolution, and we have counting numbers. Okay, so you need to be aware of all this, in which for the dimensional variables, it has a dimension. The quantities that actually vary during a given case and would be plotted against each other to show the data. And dimensional constant have dimensions, may vary from case to case, but are held constant during a given run. Okay. Pure constant are dimensionless. Okay, like the coefficient of drag or coefficient of lift, they are dimensionless. Okay, and they arise from mathematical manipulation. And later on, you will look into several other examples like the Reynolds number. Okay, for the angles and revolution, they are dimensionless. Okay, the preferred unit for an angle is radian, okay, which make it clear that an angle is a ratio. Okay, if you look into the trigonometry, you have the triangle, and from there, I believe you can see it, then can appreciate that angle is a ratio actually. Okay, counting numbers, they are dimensionless. For example, if we triple the energy E to 3E, the coefficient 3 is dimensionless. Okay. Next, we will look into this second part, which is dimensional homogeneity. Okay. This is a good example where you can't add or apples and orange together. What it means that if, let's say, if it is normally people say you must compare something that is equal or similar, right? And normally what we say is you must compare apple to apple. It is similar, like in this case, okay, where you cannot mix them up. You must look at it, you must analyze it, and make sure that they are homogeneous. Okay, a simplified expression of a far more global and fundamental mathematical law for equation, the law of dimensional homogeneity, state as every additive term in an equation must have the same dimension. Okay, again, every additive term in an equation must have the same dimension. Okay, for example, we have this Bernoulli equation on the left, right? So we have pressure, we have the kinetic energy, I would say, and it is due to the elevation. Okay, the Bernoulli equation is a good example of a dimensionally homogeneous equation. All additive terms, including the constant, have the same dimension, namely that of pressure. In terms of primary dimension, each term has dimension of mass over time square and times the length. Okay, this is the dimension of this each of these particular items on this part terms. Okay, here the units on this part is the same as this one, and also this part and this part, of course. Okay, the unit must be the same from here, here, this one, and the last one. If the unit are not the same, then you cannot add them up. That is what it means by this. Remember, means that the unit or the dimension must be the same. Okay, otherwise you cannot add them. It is here. Okay, if an equation truly expresses a proper relationship between variables in a physical process, it will be dimensionally homogeneous. That is, each of its additive terms will have the same dimension. Okay, back to our Bernoulli equation, like we have here. Okay, each term is written in terms of primary dimension, where P is this one, right? Which is the pressure, and the dimension it it is the force over area. Okay, and you can from the force, what you can see, force is actually mass times this part here is the, remember, it is the acceleration, right? Which is length over time square. And this one is actually the area. Okay, this part here is the area. And from here, you can further simplify in where you have length, and here down here you have length square, so you can take them out and can further simplify into this term. See? And also this one, where here you have a constant here, right? So just ignore, okay, this half is did not have any anything to do with the dimension, so it's just a constant, so just put it away. So, and for rho, okay, the density is mass over volume, and v square is the speed, okay, which is length over time. And here you have square, and you just put square there, no problem. And further, you can further expand this volume. Volume is actually length to the power of 3, right? There, from there, you can cancel this out. So you get this, right? Note that this one is similar to what we have up here, right? They are the same. And if you go to the last one, rho GZ, you look into this, finally, you will see that this is also the same like what we have for the previous one, right? So means that they are all are apples. Okay, they are the same. They have finally they will have the same units. Okay, because we have looked into each of it dimension. Okay, consider, for example, the change in total energy of a simple compressible closed system from one state n or time 1 to another, number 2. The change in total energy of the system, which we can say it is a delta E, is given by this particular equation. Okay. So from one state, state number 1, you have E1 equal to U1 plus KE1 and PE1. And at state number 2, you have E2 equal to U2 plus KE2 plus PE2, where U is the internal energy and KE is the kinetic energy, and last one, PE is the potential energy. Okay. So basically, they are all energy, right? And suppose they will have the same units. Okay, this component can be written in terms of the system mass, where the internal energy U, you can put it like this, and the kinetic energy is like so, and the potential energy is like so. Okay, and from there you can see that, okay, there is similarly what we have obtained just now. This one, the 3 item here, we just rearrange like this in a row. Okay, for this, we start with the kinetic energy. Okay, for the kinetic energy, it is the force. We are basically, sorry, for the energy self, this one, we start with the energy, total energy. We have is actually force times the length, and the unit is this, right? Then we move on to this part. This one, okay, it is actually mass times this part. Each of this is the same item, right? So it is energy over mass. So basically like this. And the kinetic energy, what you have is the, again, you just ignore this constant. We are only interested into this item, which is mass, and this, what are the units inside this part here, or the dimension here, which is the length square over time square. Okay, because V2 and V1 is a square, right? So that's why you have a square here. Okay, and last one is your potential energy, where you are dealing with mass, and here is the acceleration, or more specifically, it is the gravitational acceleration. And the last term here is actually the height or the length. Okay, and from here you can see that they have the same units or dimension. Sorry, they have the same units at the end of it, right? Now we look into the non-dimensionalization of equation. Okay, at some point, sometimes it is a good way or a good idea, a good approach in which we can further simplify our calculation or our analysis in such a way that we are not, we no need to deal with the dimension. Okay. The law of dimensional homogeneity guarantee that every additive term in an equation has the same dimensions. it follows that if we divide each term in the equation by a collection of variables and constants whose product has those same dimensions, the equation is rendered non-dimensional. If, in addition, the non-dimensional term in the equation are of order unity, the equation is called normalized. Okay, each term in a non-dimensional equation is dimensionless. Okay, like this. So it's being, you can call it, it is being normalized. So no units at the end of the day. Okay, right? Because on the top here you have pressure. Down here you have also pressure, but in different point, or yeah, something like that. Okay, so if you work out on this, each of it, you will get no dimension. Okay, no dimension. Okay, the two key advantages of non-dimensionalization of an equation. First one, relationship between key parameters in the problem are identified. Okay, second one, the number of parameters in a non-dimensionalized equation is less than the number of parameters in the original equation. You will appreciate this when we move to the next part later. Okay, example number 2. We have this small creature. I don't know how to pronounce it. Okay, it is a water creature or crustaceans, approximately 1 millimeter in diameter, very, very small. We want to know the drag force on this creature when it moves slowly in fresh water. A scale model of 100 times larger is made and tested in glycerin. Okay, glycerin is a kind of a fluid at a speed of 30 centimeter per second. And the measured drag on the model is obtained and shown 1.3 Newton. Okay, after this creature is being enlarged, okay, 100 times, and we test it in the glycerin, and in that particular glycerin, the glycerin have a speed of 30 centimeter per second. And from this experiment, you can see that the drag on that model, I'm talking about model, not on the original creature, but we test it on this particular model, and we get 1.3 Newton. For similar condition, what are the velocity and drag of the actual creature in water? Okay, from the model, we do this analysis and we get this amount of drag. But then from there, we want to know what is the actual drag on this particular creature in water. Okay, in our testing, we use glycerin, and in the actual, this particular creature live in water. So we know that glycerin and water surely have different densities and viscosities. And yeah, if you refer to this, you can see that for water, the density is about 1000 or 998 kg per meter cube. And for the glycerin, it is a little bit higher than what we have for the water, which is 1263 kg per meter cube. Similarly, for this viscosities, there are differences and quite high for the water and the glycerin. So assume that the model and prototype have the same Reynolds number. Okay, what is Reynolds number? Okay, in short, what I can say is Reynolds number is the ratio between the initial force and to the viscous force of that particular fluid. Okay, and we will look further detail on what is Reynolds number after this. Okay. Okay. Reynolds number, it is a dimensionless parameter. Okay. And for the approach, the length scale LM, or normally we call it this is the length of the model. M stand for model, which is 100 millimeter, and for this prototype or the actual creature itself, it is 1 millimeter in diameter, right? As mentioned here. Okay. For model, it is 100 times. So that's why for the model, it is 100, and for that particular creature, it is 1 millimeter. And from here, you want to calculate the Reynolds number and force coefficient of the model and set them equal to prototype values. Okay. The thing here is, for this particular analysis, what we need to make sure is whatever Reynolds number for the model, it must be equal to the Reynolds number for the prototype or the actual. Okay, this is the actual, this is our model. Okay, now we want to calculate the Reynolds number for our model. Okay, so for the model, we know that it is inside the glycerin. The fluid that we use is a glycerin. So the property or the density and the viscosity must taken from the glycerin, okay, which is like so. And the Vm, what is Vm? Vm is actually this one, the speed inside the glycerin, which is 30 centimeter per second or 0.3 meter per second. Make sure that the unit are in meters. Don't mix up. Okay, make sure that if the unit, you refer to the unit of length, make sure if the length is measured in meter, make sure they are all in meter. Don't mix like here you put feet, this one is meter and this one is millimeter. Don't do that. It will not work. Okay, make sure that the unit is consistent throughout your analysis. Okay, now this one is actually your LM. LM is given 100 mm or equal to 0.1 meter. Okay, and from there you can calculate, and it shows that the Reynolds number for the model is 25.3. Okay, this is your Reynolds number. And remember that Reynolds number must equal, right? They must be the same. So now you calculate your Reynolds number for the actual creature itself, where the creature is in water, and you know that the density of the water and the viscosity of the water is given here, right? Okay. So from there, you can further calculate what is the speed experienced by the creature itself. Okay. So this is the speed that you want to know, right? So you solve for VP. So you get, it is 2.53 centimeter per second. Okay. In like manner, using the prototype velocity just found, equate the force coefficient. Okay, just now we know that it moved in actual prototype or the creature, it will experience speed of 2.53 centimeter per second. So we can do the same approach to calculate the drag, okay, to measure the drag, right, on this particular creature. So from what we have found in this problem, it shows that the drag is 1.3 Newton. Okay, so the coefficient of drag is actually the ratio between the actual force or the actual drag force divided by the this set of equation rho v square times L square. Okay. Okay, for the rho for the glycerin is given here. The speed inside the glycerin, and this one is the length of that particular model. And finally, you get the coefficient is 1.14. Okay, and from there you can calculate the and everything here down here must be equal to 1.14. Okay, because CFM must be equal to CFP. Okay, they should be the same, like here. Okay, so from there, if you want to obtain the drag force on the actual creature itself, then you just plug in all these values that you have obtained. This one is the item, right, that you just obtained, and from there you know that the force acting on the actual creature is very, very small. It is 7.3 times 10 to the power of 7 Newton, which is relatively very, very small. Okay. Okay. On the third part, it is the dimensional analysis and similarity. For this dimensional analysis and similarity, okay, the motivation for dimensional analysis is actually to focus most practical fluid flow problems, which is too complex, both geometrically and physically, and to be solved analytically. Okay, they must be tested by experiment or approximate by computational fluid dynamics. Okay, experiment or where CFD or using the numerical approach. These results are typically reported as experimental or numerical data points and smooth curve. Basically, from this result of experiment or CFD, you can take it and use it as your validation. Okay, such data have much more generality if they are expressed in compact and economic form. Okay, basically, if you look into the actual problem, for example, there is a problem where apple falling off a tree, right? There are a few things involved in that particular problems of falling apples from the tree. First, you have to know that there are gravitational acceleration involved. There will be some form of air resistance as the apples go down. There will be air resistance and many others, right? The height of the initial height from where it drops or starts to fall down. So that there are a lot of things that you must take into account. So and there are ways on how to look or to analyze this particular problem. Okay, the three purpose of dimensional analysis are, the first one, to generate non-dimensional parameters that help in the design of experiment. Okay, non-dimensional parameter. Okay, and the next is to obtain scaling law so that the prototype performance can be predicted from model performance, like what we have shown in these particular examples. We have the model and we have the prototype or the actual one, right? So like this. So that is what it means by the scaling law. And last one, the third, to sometimes predict the trend in the relationship between parameters. Okay, how does it actually perform, or how does it relate between certain parameters? Okay, sometimes, for example, if you look into the relationship of velocity of a fluid inside a pipe, for example, where at certain point the velocity is high and at another point the velocity is low. Okay, let's say the point A, the velocity is very high, and at point B the velocity is low, and you can easily notify that at point A the velocity is high and therefore the pressure will be low, right? And at point B the velocity is low and therefore the pressure will be high. It must work that way for any incompressible flow, right? As long as it satisfies certain rules. And that is what been shown in the by the Bernoulli equation, actually, right? Okay, before discussing the techniques of dimensional analysis, we first explain the underlying concept of dimensional analysis, okay, which often we call it a principle of similarity. There are three necessary conditions to complete similarity between a model and a prototype. Okay, this is very important. Okay, this part is really, really important. The first one, the geometric similarity. The model must be the same shape as the prototype, but may be scaled by some constant scale factor. Okay, imagine if you want to analyze, to see the performance of an actual aircraft. The aircraft is very, very big, right? You can't fit that particular aircraft into the test section of a wind tunnel. Okay, wind tunnel, the purpose of a wind tunnel is to measure the aerodynamic performance of any arbitrary shapes or any geometry. So you can also analyze the aerodynamic performance of an aircraft. You put the aircraft on inside the test section of the wind tunnel and you can measure the aerodynamic of it. But the actual aircraft is huge. You can't actually take that aircraft and put it there. It is not economical. It is way, way too expensive if you want to build that particular wind tunnel. And therefore, what you can do, okay, is basically you can reduce the size and make a scale model of it. Okay, you scale it down to certain size where it is possible for you to fit in the wind tunnel. Okay, now the next part is the kinetic similarity. The velocity at any point in the model flow must be proportional to the velocity scale in the magnitude and mass point in the same relative direction. Okay, kinematic similarity. I know you have learned uh, dynamics in the previous semesters, and you know that what is kinematic is. Kinematic is the motion, right? So it means if the the things that you want to measure move, let's say it is rotating. So if the actual item or the actual things or the actual prototype is rotating, so that when it comes to the analysis of that model of the prototype that is rotating, you must make sure that the model also rotates in the same manner. Okay, in the same manner. The same manner means at some point it must have a certain proportion, and the magnitude must have some sort of uh, uh, must have the relative the same relative direction. If it is rotating to the left, then you must make sure that the model also rotating to the left. If uh, it has certain kinematics. Okay, the third one must have the dynamic similarity. Is achieved when all forces in the model flow scale by constant vector to corresponding force in the prototype flow. Okay, the dynamic of it must be the same. Okay, the first one is the geometry, second is the dynamics, and the third is the dynamics. Okay, dynamic similarity. I think later you will appreciate more on this part where you are going to analyze the forces acting on an aircraft, where it covers in aircraft performance analysis. Okay, or we call it flight mechanics later on. Okay, dimensional analysis and similarity. The first on the top we have the prototype. Okay, VP, P stand for prototype, and M is for the model. And you can see from here that each of these box, okay, the orientation, okay, the location of it must be the same, right? Okay, so the size, the geometry must be the same. So as we know that the geometric similarity, you need to have this, right? Geometric similarity, right? So does have that. And the kinematic similarity is achieved when at all locations, the velocity in the model flow is proportional to that at corresponding location in the prototype flow. See this direction. Okay, going up, and on this one, it's going down. So that is what it means. Okay. Okay. Now, this is more interesting. We let the uppercase Greek. This is what we call uh, later on we will look into this pi theorem. Okay, now we just want to highlight what is this term is really is. Okay, pi denote a non-dimensional parameter in a general dimensional analysis problem. There is one pi that we call the dependent, giving notation of pi1. The parameter pi1 is a general. It is in general a function of several other pi's, which we call independent pi's. Okay, functional relationship, you can rewrite it as like this. To ensure complete similarity, the model and prototype must have geometric similarity, and all independent pi groups must match between model and prototype. Okay, pi model equal to pi prototype. Previously, I have shown you the Reynolds number of a model equal to Reynolds number of a prototype. This and this is the pi. Okay, this one. Okay, pi can be anything. Reynolds number. It can be a coefficient of drag. Can be a coefficient of lift, and many other things. Okay, that you will see later. Okay, dimensional analysis and similarity. Okay, this is another example. We have the viscosity. Okay, we want to determine the dimension of viscosity, where this is the process. Of course, you just rearrange this equation, right? So from there, you can further analyze it using the dimension analysis to look into each of the component, the dimension, the primary dimension of each of these element, force, area, velocity, and length. So, and finally, you will obtain this dimension, set of dimension that you can further transform that into units. Okay. This is another example. Okay. This is example where the aerodynamic drag of a new sports car is to be predicted at a speed of 50 miles per hour at an air temperature of 25 degrees Celsius. Automotive engineer built a 1/5 scale. So the actual car, let's say the actual car length is 5 meter, and then you can scale it down to 1 meter. Okay, that is what it means by this one lah. And you can put it in the wind tunnel. It is winter, and the wind tunnel is located in unheated building. Okay, it gives us one information here that is very important, where at the time of the testing, okay, in that area or in that region, it is winter time, so the temperature is very low. Okay, temperature at that time is only 5 degrees Celsius. Okay. Okay, determine how fast the engineer should run the wind tunnel in order to achieve similarity between model and prototype. So this is the challenge. The first one, remember that the size of the actual car is being reduced. Okay. And the temperature during the testing is not the same like what being experienced by the actual car. Okay. So the viscosity and the density of the air is different. So you need to take into account on these two differences. Okay. So it is list of assumption, and it is the properties of air at 25 degrees Celsius and during testing at 5 degrees Celsius. So from here, you will use the Reynolds number. Okay, the same approach that I have shown you just now. Okay, using the Reynolds number. It is the actual car, and it is the model of the car, which is 5 times smaller. Okay, first we must make sure that the Reynolds number are the same. Okay, the pi must be the same. So this is the equation, and then from there you can rearrange this to get the value of this v, right? Speed of the model. So from there you rearrange and you get this equation. and plug in all the values, and finally you will get this speed. And the second example, almost the same example actually, but the arrangement is different. I hope you can look into this example on your own and appreciate what are the changes.